Now we're moving on to the stuff that really deals with statistics, the notion of significance, and then its related notion of power. Power we won't concentrate on too much. For those who encounter it later, maybe if you have graduate studies, it's important. I'm going to gloss over it really quickly. Significance is what we're going to be focusing on. And the basic idea behind significance, besides all the stuff with normal approximations or bell curves, and your sigma levels, your confidence in all that, is this notion of statistical results being significant. Significance is a technical notion. Okay, so remember we're dealing with the frequency interpretation. There's no probability of a hypothesis being true. It's either a fact or it's not. So the frequency interpretation says if you say something is 95% certain, you're not saying, I think it could happen, but maybe not. You're saying, for instance, out there in the world, if there's 100 people, 95% certainty means 95 people fit this bill out of 100 people, or 95 objects fit this whatever description out of 100. So the 95 out of 100, 95% represents a frequency, an amount. This is in direct contrast to Bayes. Using our previous example from a previous lecture, remember the claim that 90% will arrive unbroken and 10% will be damaged in some way. The probabilities of 90% represent frequencies about the world. So UPS in this hypothetical case actually has past records on shipments of these ornaments, and out of, let's say, 1,000, 900 arose unbroken. So that's where the 90% claim comes from. It's not about a hypothesis. It's either simply true or false of the world, and that's what frequency interpretation indicates. Okay? The data on UPS is significant at the 1% level. What does this mean? This is the language, the jargon used in significance talk. The 1% level is actually talking about, it inverts things. So if you see 5% level, they're really talking about the 2 sigma, which is the 95% range. And if you talk about 1%, they're really talking about 3 sigma, the 1% level. Okay? What it says is that if O, your hypothesis about ornaments, is true, the probability of unbroken ornaments is that you get something outside of the 3 sigma range. So in this case, it's when you calculate it, either less than 2,652 or more than 2,748. Basically, all these numbers are saying is once I calculated mu, the theoretical mean, and then sigma, and then I multiplied sigma by 3 to get the 3 sigma, which gives me the 99% range. The chances of it falling outside of this range, outside of 99%, is only 1%. So if you got something out of this, either you had a freak occurrence, which only occurs 1% of the time, or your hypothesis that that UPS advertises that 90% arrive unbroken, it's false. So either you got unlucky, or the hypothesis is false. What does that mean? Well, let's step back a little bit. So here's how statistics are basically run. So if you got, say, a drug trial, right, which is what you need to get a drug on the market, you got to basically set up a statistical model. This is beyond our course. It's basically the way in which things are modeled, your experimental setup, and then what kind of probability model you're going to use. So don't worry about one. That's basically just what you need to do. And secondly, you split your group into 2. If you want to know if your drug works, you have a placebo group, basically a sugar pill, right? It's not a real drug, and then those who receive the drug. And what you hope for when you set this thing up, if you do it properly, is you expect or hope for a difference. Those who take the placebo, which is the fake pill, right, should not see any difference in whatever condition they got. And those who take the real pill, if the pill has real causal powers, which is what you want, you expect to see some kind of difference. They recover or they get better or something, but you can measure it, right? So why you split it in 2, it gives you a binomial distribution, and you can model then your drug trial as a Bernoulli trial. Why binomial? Because either you split them in 2, and it either makes a difference or it's not. It's like heads or tails. In this case, true or false. It makes a difference or not. Okay. Third, you define a null hypothesis. The null means nothing, 0. So the null hypothesis in this case is the drug makes no difference. It does not work. Okay. 4, you run your experiment and you measure differences in results, however you're going to measure that. And then, lastly, you set up your experiment such that according to your null hypothesis and your statistical model, there's a low probability of, you basically specify what's called your P level. So if you're doing it at 1%, then you're saying you're doing it at the 3 sigma level. Other types of standards in other fields will specify this different. If they do the 10%, and you're going to see this in the upcoming quiz, 10% level, what they're talking about is 90% interval, which is somewhere between the somewhere between the 1 sigma level, remember that's 68, and 2 sigma, which is 95. The weaker this thing is, that's to say, if it's 10% or 5%, the easier it is to get your results. And this is one of the ways in which you can sort of tweak your statistics, which happens very often to get the desired result. So statistics is remarkably easy to manipulate, and it very often is in political and scientific contexts. That's an unfortunate truth of this stuff. But the mathematics and the logic of it, if it's done correctly, is very powerful. But that's a big if. Yeah. What this all means when you sum it all up is, if your drug works, you hope for a big difference or some measurable difference between the control group, which should have no change, and the drug group. Maybe they're cured or they're better. But maybe, just maybe, the way in which you gathered your sample population, remember, you can't run this drug and test on everyone. You got to do it in small groups, right? And you're hoping then that this reflects something in the general population. Maybe you got unlucky, right? And they were naturally going to get cured of their own powers. The drug itself, let's suppose, doesn't work, but you give them the real drug and they remarkably get better just because they're already super healthy, right? So what you're saying when you talk about significance is basically a correlation between your measured result, but not whether or not, in this case, the drug actually works. You don't know that. Cause is what you want, but cause is hard to establish. It's really hard. All the sciences aim for causes, but tracking actual causes is very, very hard. Correlations give us basically things that are related to one another in some way, and from there we hope that it indicates a causal relation, but we don't know that. So all you can say in this case is either your null hypothesis is true, meaning that the drug has no effect, right? In which case something unusual happened. How often does it happen? In only 1% of the cases. 1%. It's outside the 99%. So you get the extreme, the 1% in this case is the extreme group. You got unlucky in choosing the super healthy people who are going to get better anyway, right? So either, in this case, either one, the drug really doesn't work. The null hypothesis is true. The drug doesn't work. And the reason people got better wasn't because of the drug, but because you got really unlucky in picking this group of people that were going to get better anyway, which only happens in 1% of the population. Really, really unlucky. Or, the flip side, what you're inclined to buy, the null hypothesis is false. The null hypothesis being false, meaning the drug may have some powers that work. Okay? The drug has an effect. So that's the way in which you couch these conclusions. Significant levels, basically all this stuff, they're called P levels. Previously I said that correlations are not causes, meaning, well, if you haven't heard that before, let's use a concrete example. Barometer is often used. A barometer is correlated with weather, right? Why? Well, if there's a change in weather, the barometer indicates that. However, it would be a mistake to say that because there's a correlation there, that one causes the other as such. There is a causal relation. There is both a correlation and a causation. The correlation is between the barometer and weather. The causation is between the weather patterns and the barometer. It is not a reverse causal relation. The barometer does not cause changes in weather. Correlations, therefore, are weaker. They're only related between things. But it doesn't indicate any actual causal relation. If you want something a bit more exotic, they have these studies, and I mentioned this before, the science of so-called beauty, or the so-called science of beauty. And when they say, look at you hold your hands up, and you put them together, right, your fingers. They find that if your ring finger is longer than your first finger, that indicates that you have greater symmetry and thereby are more likely to be better looking overall. And they find that there's a correlation here between people they've measured who have this asymmetry in their fingers, a longer ring finger and a shorter, was it index finger, the first one? They find that indeed they tend to be more beautiful looking, whatever that means exactly. But the problem here is you have a correlation. Is there any cause between this? I mean, is there any reason why, a causal relation as to why having this disparate finger length relates somehow to being more beautiful? Not necessarily. It seems like this is an interesting correlation at best, but causal, it's hard to figure that out, if there is any. What the tests really are saying is we establish some correlation, say with the drug test, right? And we think maybe the drug works if you get the results you're hoping for. Basically things that fall, in the 1% level, outside of your 3 sigma. That means when you think about it, there's a big difference, okay? But what it really says is we have an initial correlation. We really don't know what the heck is going on. These tests point the way to further research that needs to be done. Graphically, you can think of it like this. You have your placebo group. You give them the drug. You expect no difference after the trial, right? So no measurable difference. If this is where they measured at the start, at the end they should be within that, maybe slightly better because some people feel like they got better, psychosomatic effect, but you expect your placebo group has no difference. So the measurable difference, none. Whereas those who get the drug, you hope for a big difference. This is the measurable difference. How big? Outside of the 3 sigma. So this is the 1%. 3 sigma, remember, is 99% of the cases. But the 1% here represents a big difference. And if you got your drug group there, a measurable difference between them and the placebo group, you expect, you hope, that the drug is the thing that made a difference. But again, you don't know that for sure. Your inclination is to say the drug works, but you don't know that for sure. Because again, you could have gotten lucky and got the 1% of the population that was going to get better on their own anyway. Okay? Power says more than significance. Power is basically like significance on steroids. There's two. I'm going to go through this quickly because again, it's pretty hard to get through. It's important at higher levels. You should be aware of it, but we're not going to get tested on this or anything like that. So there's two types of errors: rejecting a hypothesis, which is when it's true, right? And the problem is when you get correlations, you can err in several types of ways. In general, two types of ways. You can commit an error of type 1. You reject a hypothesis when in fact it's true. Or in type 2, you accept hypothesis when it's false. You accept that the drug works because you reject your null hypothesis. But what if in fact it was, again, you got unlucky in your group. You didn't retest your experiment. You only ran it one time. You got unlucky in your sample group because you got the super healthy people. You didn't retest, let's say, 100 times with different groups, with different people from different backgrounds. And then, if you had done that, you might find that, oh, in 99 of those 100 cases, I get no difference. Only in that one case I ran did I get a big difference, but that's because of the people. When that happens, you're inclined to think, hey, this drug doesn't work. So that's an error of type 2 that's most often committed when you have significance. You accept the hypothesis when in fact it's false. The other one, type 1, is sort of like the reverse of that, rejecting a hypothesis when in fact it's true. What power does is it basically says you want to maximize the power of tests, you want to maximize the chances of rejecting a false hypothesis, okay? So power tests basically minimize the probability of rejecting a true hypothesis and in addition maximize the probability of rejecting a false hypothesis. This is the type 1 and type 2. Don't get what this says, don't worry about it. The next chapter on confidence basically is equivalent to power. When you talk about power, you're talking about something that's a stronger significance test, and confidence intervals, which comes up next chapter that we'll be talking about, is basically building that in. I'm not going to explain how that works. Don't worry about it. But roughly speaking, that's the idea. Okay, that's it for this lecture. The homework is basically mainly a conceptual one. The quiz is mainly a conceptual guide through these ideas, and then the homework after that is more sophisticated, and it's testing your understanding of these concepts.